Okay, expectation. We're going to be talking about, okay, what we've got these distributions of random variables. Over time, if we run the experiment over and over and over again, what do we expect that random variable to have on average in the long run? Here's a kind of a simple one. You're going to roll a die a whole bunch of times. How many times do you expect it to be a 6? Well, you'd expect it to be a 6 1/6 of the time, right? Because there's 6 different possibilities, they're all equal to happen. So 1/6 of the time you expect to be a 6. So out of 120 rolls, we would expect 20 of the times to be 6s. That's kind of simple. We have a discrete random variable, and we talk about this, doing this millions and millions of times. What do we expect the average of this to be over and over again? Oh, sorry, I skipped example 5. Same kind of thing. You're going to kick 12, I guess it sounds like penalty kicks. You kick 12 times. You have a 3/4 chance of getting each one. You would expect 9 of those to go in because you expect each one would have 3/4 of a chance. So over time, 3/4 of the 12, and of means times, of course. So 3/4 of 12 should go in. So that would be 9, I believe. So same thing here. So we expect if we roll a 1, we're going to get, it's a square spinner. Okay. If we spin a 1, we get $1. If we spin a 2, we get 2. And these are all equal chance of happening. So a quarter of the time, what they didn't talk about here was the probability of each one of these things happening. This is each, sounds like it's each a quarter. That's kind of important. What's the expected return for one spin of the spinner? Well, really, if they all have equal chance of happening, a quarter of the time, we're going to get 1. So that's going to kind of contribute that much to our average. A quarter of the time, we're going to get 2. That's a times. A quarter of the time, we're going to get 5. And a quarter of the time, we're going to get 8. We add those up. I'm guessing the answers are on the next page because I have a little thing there. Oh, yeah, that was the answer to the football one. Yeah, a quarter of the time we're going to each one of those ones. So over time, that adds up to 4. So on average, we would expect 4. That would be the same thing, actually. If you added up 1 plus 2 plus 5 plus 8 divided by 4, you'd get 4. Yeah, because that adds up to 16. Yes, it does. But you can also do it this way. Like a quarter of the time, it's going to turn out to be 1. A quarter of the time, it's going to turn out to be 2. So a quarter of 2 is what you expect per spin. A quarter of 5 is what you expect the contribution from 5 per spin. This is kind of a more sophisticated way to think of that. Rather than adding them all up and dividing by 4, this is a little bit more applicable to what we're about to do. So I encourage you to try to think of why this works. All right, and then the next question is, well, would you play this game if it cost you $5 to play? No, in the long run, that's a bad idea because you expect to get $4 from this game on average, even though, of course, you can't get exactly 4. You expect the average return on this game to produce $4, so you shouldn't pay $5 to play it. If they ask you to play this game for $3, sure, play it for $3 and keep playing all day. You'll probably come out ahead. All right, but for $5, you'll lose. All right, so for examples like example 6, that would be this one back here. We're saying that the expected value, and they use a great big E there, like, kind of like probability, but they're using E for expected value, of the random variable is the sum of all the probabilities, and that's what we were doing here. It's the probability that each one of these things will happen times, so the probability of that will happen times the value you're getting in the random variable. That's going to be the expected kind of total average per turn you're going to expect to get from the random variable. Okay. A particular region, the probability it will rain is 28%. How many days of the year do you expect it to rain? Well, we'd expect it to rain on 28% of the days in a year, whatever that is. If 3 coins are tossed, what's the chance they all fall heads? We've done this before. If the 3 coins are tossed 200 times, how many times do you expect them to all be heads? Probably about that much. 2 dice are rolled simultaneously, well, the same as rolling one of the other. 108 times, how many times do you expect to get a double? Well, you expect to get a double 1/6 of the time, so how many times out of 180 would you expect to get doubles? Well, 1/6 of that. Single coin is tossed once. If a head appears, you win $2. If tail appears, you lose $1. How much do you expect to win when playing this game 3 times? Well, each time you play it, you expect to get $2 for the heads, and you expect to get negative $1 for the tails. So this is the average for each roll, each flip of the coin, which is 1 minus a half, which is a half $1. If that's going to happen 3 times, so it's just, now it's like this part, I'm kind of doing the same thing I did up here. You expect to get $1.50. You expect to get 3 halves of $1 after 3 times. So I guess another way to call that is $1.50. Yeah, okay. Answers are over here. No, the answers are on the next page. Here's some more questions. During the snow season, there's a 3/7 probability of snow falling on any particular day. If Udo skis for 5 weeks, that's 35 days. How many days could he expect to see snow falling? Well, 3/7 of those days it should have snow falling, which is, I think, 15. In a random survey of electorate, politician A discovered residents' voting intentions in relation to herself and the 2 opponents. Sounds like something coming up. Okay. Estimate the probability the randomly chosen voter in this electorate will vote for blah, blah, blah. Well, I think we have to know the total of that. I don't really want to do that in my head. Oh, the answers are coming up. For 6, it doesn't have the totals, but it figured out the percentages. It basically changed these into percents. To change these into percents, you have to know the total. The total is... Oops, how did that happen? Oops, sorry about that. To move the frame here. Something moved. Just a second. All right, sorry about that. The total here is 300. If you add those up, so this is like 55%. This is, okay, I'm going to cheat again. It was 55% and 29 and 16%. Okay. So that's how they got 29% and 16%. That's how they got these 3 totals. If there's 7,500 people in the electorate, how many of these would you expect to vote for? So this is like a sample. So she just took a random survey. So she took just 300 people. If you were to scale it up to 7,500 people, well, guess what? You'd have to just take these same percents. It's just like we were doing on the last page. You take 55% of 7,500. That's not too hard to imagine, etc. The answers on the next page. Person rolls a normal 6-sided die and wins the number of dollars shown on the face. How much does the person expect to win for 1 roll of the die? Well, 1/6 of the time you expect that to be a 1. 1/6 of the time you expect it to win $2. 1/6 of the time you expect to win $3, etc. What's the average of? Well, let me show you how they work this out on number 7 here. They don't even show you. Okay, fine. So for rolling the dice, you'd expect 1/6 of the time you're going to get $1, 1/6 of the time you're going to get $2, etc. That adds up to 3.5, actually. The average roll on the dice is 3.5, if you didn't know that. If it costs $4 to play the game, should you play the game? No, because in the long run, you're going to get back $3.5 each time. So that's a bad idea. Charity fundraiser gets a license to run the following gambling game. If a die rolls and turns these numbers, you get these dollars. Okay, what's your chances of playing one game and winning? $10. Well, that's only going to be 1 out of the 6 times. You have to roll a 6. $4, that's 2 of the 6. And $1, that's 3 of the 6. Your expected return from throwing a 6 is, of course, that. What's your expected return of throwing a 4 or a 5? What's your expected return of throwing a 4 or 5? That's right out of the chart, isn't it? That's just $4, $1. Oh, 1, 2, 3, 4, 5, or 6. Well, that's going to be all these probabilities added up. So it's 1/6. Let's go from the top down. That's 1/6 of the time you're going to get 10. 2/6 of the time you're going to get $4, and 3/6 or half of the time you're going to get $1. Whoops, that's a times. 3/6 of the time you're going to get $1. What's your overall expected result at the end of the game? That should be that. How many times are we playing this? It doesn't say. At the end of, 1 game. Sorry, if we play 1 game, it would be the total of that. What are we on here? 8B, 8C. 8B3 was $3.50. So if it costs you $4, does it cost you $4 to play? It says that, $4. So we expect to get, this is $3.50 again. You expect to get $3.50. So if it costs $4 to play, you're going to lose 50 cents here. What's your overall expected result of 100 games? Well, that's going to happen on average for each game. So if you do that for 100 games, you're probably going to lose $50. You're going to lose 50 cents each game. So if 100 games, you're going to lose $50. Person plays a game with a pair of coins. If 2 heads, you get $10. If a head and a tail appear, it's $3. If 2 tails, then you lose 5. Let's make a table for this. So if it's, we could do it this way. If you get heads, then you get 10. And let's talk about how much money you get. If you get 1 of each, I'm going to write it this way because it's not exactly heads and tails. It's heads and tails or tails and heads. you get 3. And if it's tails, tails, it's -5. I don't have enough room here. What's the probability of this? We talked about this already. This is 1/4. Oh, that's really small. One of each, that's 2/4. And tails, tails, that's 1/4. So it's like half here. Sorry, quarter, half, quarter. How much should a person expect to win playing the game once? Well, it's a quarter. Probability you're going to get 10. It's a half probability or 2/4 probability you're going to get 3, plus a quarter probability you're actually going to get -5 in winnings. What is that altogether? I'm going to cheat. 9 A's, $2.75. It's positive. Well, that's good. You're going to get $2.75. The organizer is a game allowed to make an average of $1 per game. How much should you charge? The organizer of the game is allowed to make an average of $1 per game. So that means I think the house is supposed to get $1 per game. So you could charge $1.75. Oh, I read that the wrong way. So you could charge, sorry, the dollar's going the other way. The organizer of the game is allowed to make an average of $1 per game. So, oh yeah, so you should charge $3.75 if you're planning to hand out $2.75. That was my fault the first time. Okay. Oh, and I think that's it. Oh my gosh, you guys, we made it all the way through the whole thing. Okay, I'll see you in class. And yeah, there'll be another video after the quiz, but this is all that's on the quiz. And actually, the quiz is not as hard as I thought it would be. Anyway, you'll be fine. This is as far as the quiz goes. Okay, I'll see you on quiz day.